So in today's video, we are going to focus on unbalanced three-phase systems. An unbalanced three-phase system is caused by two possible situations. One, if the source voltages are not equal in magnitude and or differ in phase by angles that are unequal. And then secondly, if the load impedances are not equal. Now in today's video, we are going to consider a situation where the source voltages are balanced, however, the load is unbalanced. So let's get into today's lesson. So we have three balanced source voltages, or better still, phase voltages. We have this to be Van, Vbn, and then Vcn. And then we have this to be the neutral point. Now this is feeding an unbalanced star connected load of phase impedances Za, Zb, and then Zc. Now since the load is unbalanced, then it means that the phase impedances Za, Zb, and then Zc are not the same. So let's assume that we have Ip1, Ip2, and then Ip3 to be the phase currents for the respective phases. And then also we have Ia, Ib, and then Ic to be the line currents, as well as In to be the current in the neutral line. Now since the phase impedances are not the same, it means that the phase currents are also not the same. So how do we find the phase currents for the respective phases and hence the current that flows through the neutral line? So to find the phase currents, we know that the phase current is giving us the phase voltage divided by the impedance per phase. So for this case, we have the phase current Ip1 to be equal to the phase voltage, which is giving us Van, divided by the phase impedance Za. For the second phase, we have Ip2 equals Vbn divided by Zb, and then we have for the third phase Ip3 equals Vcn divided by Zc. So these are the phase currents for the respective phases, and incidentally these phase currents are equal to the line currents Ia, Ib, and then Ic. Now to the value of current flowing through the neutral line. So how do we find the current In? We are going to apply KCL at the neutral point at the load. We have all the currents flowing in one direction to meet at this point. So from KCL, we have Ia plus Ib plus Ic plus In equals 0. Now notice that if the load was balanced, then we have no current in the neutral line. However, since the load is unbalanced, then we have some current flowing through the neutral line. So we need to find that current. So to find the value of current flowing through the neutral line, that is giving us negative of the sum of all these current values, Ia, Ib, and then Ic. So basically, the current that flows through the neutral line is equal to the phasor sum of the three line currents, that is Ia, Ib, and then Ic. And the negative only indicates the direction of In. So having obtained this knowledge, let's move on to solve a few examples. So for example 1, determine the load current if the supply voltage is 415 volts and then Z1 equals 8 plus J0 ohms, Z2 equals 0 minus J8 ohms, and then Z3 equals 0 plus J8 ohms. So this is a very simple problem. Let's try to solve this problem together. So in the question, we are given the supply voltage to be 415 volts. Now the supply voltage is the same as the line voltage, and that is giving us 415 volts. And then we are asked to find the load current in this particular circuit. Now the load current happens to be the current in the neutral line, or better still, the neutral current. Now to find the load current, we first of all need to find the current in each phase. Now the current in each phase is giving us the phase voltage divided by the impedance per phase. So what this primarily means is that we first of all need to find the phase voltage. Now because this is a star configuration, we know that the line voltage is giving us √3 times the phase voltage, and in that case the phase voltage is equal to the line voltage divided by √3. Now in the question, we have the line voltage to be 415 volts, so that is 415 divided by √3, and that is equal to 239.6 volts. So this is the phase voltage. So now let's move on as we find the phase current for the respective phases. So we have the phase current for the first phase giving us Ip1 equals the phase voltage, and in this case we are going to consider the first phase voltage to be the reference phase voltage. So that is 239.6 polar 0, now divided by Z1. Now here we have Z1 to be 8 plus J0 ohms. Now 8 plus J0 ohms, converting this from the rectangular form to the polar form, gives 8 polar 0. So 239.6 divided by 8 gives 29.95, and then 0 minus 0 is 0. So we have the phase current Ip1 to be equal to 29.95 polar 0. Now let's move on to the second phase, that is Ip2, and that is also equal to 239.6, and this time polar negative 120 degrees divided by the impedance Z2. So we have Z2 to be 0 minus J8 ohms, converting this to the polar form, that is equal to 8 polar negative 90 degrees. 239.6 divided by 8 gives 29.95, and then negative 120 minus negative 90 is the same as negative 120 plus 90, and that is equal to negative 30. So this is the value of current in the second phase, and then we move on to the third phase, that is Ip3, and that is equal to 239.6 polar. This time we have plus 120 divided by Z3, and then converting this to the polar form, that's going to be 8 polar 90. So dividing 293.6 by 8, you have 29.95 polar 120 minus 90, and that is equal to 30. So these are the phase currents in the respective phases, and then they are also equal to the line currents. Now to find the load current, or better still the current in the neutral line, we are basically going to add the phasor sum of the three current values that we have here. So the load current, which is giving us the current in the neutral, is equal to 29.95 polar 0 plus 29.95 polar negative 30 plus 29.95 polar 30. Now because these are all phases, we can group them into their x and y components, that is the real and imaginary components. So for the real component, which is called the x component, we have 29.95 cos 0 plus 29.95 cos negative 30 plus 29.95 cos 30 So 29.95 cos 0 is the same as 29.95, and then 29.95 cos negative 30 is 25.94, and then we also have 29.95 cos 30, that also gives 25.94. Now adding all these three values, we are going to get 81.83. So this is the value of the x component, or the real component. So for the y component, or the imaginary component, you have 29.95 sine 0 plus 29.95 sine negative 30 plus 29.95 sine 30, and that is equal to, now 29.95 sine 0 gives 0, 29.95 sine negative 30 gives negative 14.98, and then 29.95 sine 30 also gives 14.98. So adding all these three values, then we are going to get 0. Therefore the current in the neutral, that is given by In, in the rectangular form is giving us the x value, or the real value, 81.83 plus J0, and then converting this value to the polar form, that's going to give you 81.83 polar 0. So this is the value of current flowing through the neutral line. Mind you, the negative only indicates the direction of the current. So we have In to be equal to 81.83 polar 0 degrees. Now let's move on to the next example. So now to example 2. In a 3-phase 4-wire system, the line voltage is 400 volts and the resistive loads of 10 kilowatts, 8 kilowatts, and then 5 kilowatts are connected between the 3 lines and neutral. Calculate A, the current in each line, and then B, the current in the neutral conductor. So according to this question, we have the line voltage, that is VL, to be 400 volts, and then we are given the resistive loads of power, that is 10 kilowatts, 8 kilowatts, and then 5 kilowatts. So basically these are the power associated with the resistive loads per phase. So let's assume that we have the 10 kilowatts power to be the power associated with the resistive load in the first phase, and also we have P2 to be 8 kilowatts, that is the power associated with the resistive load at phase 2 or in phase 2, and then also for P3, that is equal to 5 kilowatts, and that is the power associated with the resistive load in the third phase. Now these power values that we have are the power associated with the impedance or the resistive loads per phase. And then we know that power is giving us the current times the voltage times cosine of angle phi. Now because we are dealing with resistive loads only, then it means that cos of angle phi is equal to 1. So we can just leave that one out, and then we are left with P equals IV. Since this power is given per phase, then it means that we have the current also per phase and also the voltage per phase. So if we want to find the current per phase, then we need to make sure that we have this voltage, or we have the voltage per phase. Now we are given the line voltage to be 400 volts. Let's try to find the phase voltage. So because we have a star configuration, the phase voltage is nothing but equal to the line voltage divided by √3, and that is equal to 400 divided by √3, and then we have the phase voltage to be equal to 230.94 volts. So this is the value of the phase voltage. Now since we have the value of the phase voltage, we can find the value of the phase current. So we have the phase current IP to be equal to the power, that is per phase, divided by the phase voltage. So let's start off with phase 1. So that's going to be IP1 equals P1, which is 10 kilowatts, so 10 times 10 exponent 3 divided by Vp, which is 230.94. Now because we are considering the first phase, then we are going to consider this voltage to be the reference voltage. So that is 230.94 polar 0. Now 10 times 10 exponent 3 divided by 230.94 gives 43.30, and then we have the phase angle here to be 0 because the impedance is solely resistive. So that's going to be 0 minus 0, and that is still 0. Now let's move on to phase 2. So for phase 2, we have IP2 equals P2, which is 8 times 10 exponent 3 divided by 230.94. This time, because we are dealing with phase 2, we have the phase angle of the voltage to be negative 120. So 8 times 10 exponent 3 divided by 230.94 is 34.64 polar. 0 minus negative 120 is going to be positive 120. And then for phase 3, we have Ip3 equals 5 times 10 exponent 3 divided by 230.94 polar 120, and then 5 times 10 exponent 3 divided by 230.94 gives 21.65, and then we have 0 minus 120, that is negative 120. Now, because these phase currents can be said to be their respective line currents, then we say that we have the first one to be Ia, the second to be Ib, and the third to be Ic. So these are the line currents. Now let's find the current in the neutral conductor. So that's giving us the phasor sum of the 3 line currents, Ia, Ib, and then Ic. So that's going to be 43.30 polar 0 plus 34.64 polar 120 plus 21.65 polar negative 120, and then adding these phases, we are going to get 18.87 polar 36.588. So this is the value of current flowing through the neutral conductor.